Now these rules that are in your data booklet, they will always work. So these rules will always work. Data book. Equations will always work. But there is something screwy about them. So let me show you that. The convention must always be that your theta starts from this direction around this way to your vector. And so to just kind of show you some examples of how that gets a little screwy is if we have our axes this way and we want to measure a vector in this direction, then to find its x and y components, so its x component off this way and its y component up this way, to find its x and y components, I would have to use the angle theta that again starts here and goes clear around to the vector. So in this case, theta is going to be more than 90, all right? Likewise, if I have a coordinate like this, and I have a vector that is going down diagonally this direction, I have to represent theta as this angle from that angle there. So theta is going to be more than 180 in this case, right? And sometimes it's awfully inconvenient to do that because let's say they give you this angle in the book. Let's call that angle phi. Then you'll have to figure out that theta is equal to 270 minus phi or whatever, right? In order for the data booklet equations to always work, you always have to use the same convention for theta, right? So these equations will always work as long as theta always begins, one more example here. If we have a vector that they tell you is just below the axes this way, well then theta is going to be, like 330 degrees or something. It's going to be almost all the way around the circle. If you use theta is equal to, if they tell you that this angle here is 30 degrees, then you have to say that theta is equal to 330 degrees. And in order to find the x and y component of this vector, let's say we call this vector b, well, in order to find what is bx and what is by, in order to find those, I'd say that bx is equal to whatever b is. Well, let's give it a number. If b is 10 meters, all right. Well, then bx is going to equal the magnitude, right? So it'll equal, bx will equal 10, that's the magnitude of the vector, times the cosine of theta, but theta has to be this 330, right? 10 times the cosine of 330. Well, let's crunch it out. We have 10 times the cosine of 330 degrees. That's 8.6 meters. And by is going to equal 10 times the sine of 330 degrees. All right, 10 times the sine. 10 times the sine of this 330 degrees. And that gives me -5. Well, that kind of makes sense, that this vector is going over to the right and down, so that bx is going to be a positive 8.6, and by is going to equal a -5. All right. Next, reconstructing vectors. So let's talk about reconstructing vectors from their components. before I step into reconstructing vectors from components, back to this idea for just a second. Because of this complication around theta and not starting with, whatever this convention is where you have to use theta starting from this angle, some people prefer to use SOHCAHTOA, and that I'm in that boat as well. I prefer using SOHCAHTOA when solving for the components of vectors. So if I have a vector that is, let's say, this direction, and they give me that this vector is 5 meters long, and it's at an angle here of 20 degrees, let's say, even though that doesn't look like 20 degrees, but let's imagine with me. If I wanted to solve this problem and find what are the x and y components of this vector, what is the component? It is up how far, and it is over to the left how far, right? So what is this x component and what is this y component? Well, let's say this vector is A, and we're going to call this A sub x and A sub y. The way I like to do this is SOHCAHTOA. I like to set up a triangle here. I have a triangle set up, I guess, where there are 3 sides of this right triangle. I know that this side is the hypotenuse. If this is where my angle theta is that I'm going to set up, then I could find the 2 other sides for SOHCAHTOA. There are 3 sides to the triangle you have to label. So step 1, if you want to call it, would be like label the sides. I like to first label the hypotenuse. Second, label the opposite, OPP let's call it, if you're down with that. And third, label the adjacent side. And that's the one that's left. Alright, so the rules here is like the hypotenuse, that's obviously opposite the 90-degree angle here, the longest side, it's the longest word. Second is the opposite side. When they say opposite, what they really mean in solving SOHCAHTOA, and you probably remember this from math class, it is the opposite from theta. It's the opposite side from theta. So if you know where theta is, the opposite is on the opposite side of the triangle from theta. Right? And then after you have those 2 labeled, the third one I always have is adjacent because that's the one that's left. It means next to, but there are 2 sides next to. So I always leave adjacent for last because of that. Once I have this set up, if I know that my hypotenuse has a length of 5, and I know my theta is 20 degrees, then I can use any one of these 3 equations, SOHCA or TOA, to find the other sides of my triangle. I might find the opposite side next. That would be my y component, and I would say that this SO stands for that the sine of theta is equal to the opposite over the hypotenuse, and I know that my theta is 20 degrees, so I say that therefore the sine of 20 degrees is equal to the opposite side, which I'm calling AY, over the hypotenuse, which I know is 5 meters. And then I can solve this, that 5 times the sine of 20 is equal to AY. So AY is equal to 5 times the sine of 20 degrees. And geez, I think if you use the equations from the data book, you're going to get the same number that I get from this calculation here. And that is that the AY would be, well, let's crunch it out here. 5 times the sine of 20 gives me 1.71. And I could likewise, so this is finding the AY, I could likewise find AX. See, AX is, well, AX is my adjacent side. So to solve for my adjacent side, I would use this CAH. That's that the cosine of theta is equal to adjacent over hypotenuse. And then I'd say that the cosine of 20 is equal to the adjacent side, which is AX in my problem, over the hypotenuse, which is 5 meters. And that then, therefore, AX is equal to 5 times the cosine of 20, which gives me 5 times cosine of 20, 4.7 meters. All right. Okay, so you can use either system for resolving a vector into its components. One is the data book, these equations that they give you, and always remembering that your angle theta has to start from this point here. So if you're using that system, you could do that. You just have to say that if this angle is 20, then your theta has to be 90 plus another 20. So your theta would have to equal 110 degrees if you're going to use the data book's equations. Or you can scrap those and use SOHCAHTOA if that's something that you're familiar with. And I think that that works well too. So it's your decision there. All right. Back to reconstructing vectors from components. This is kind of the last idea that we need to get across here. And it goes something like this. If I were to tell you that AX is equal to 25 meters and AY is equal to 16 meters, well, you can kind of picture what our vector might be looking like. Here, let's draw our coordinate axes. And if AX is 25 meters, that's saying that the X component of our vector that starts here at the origin has to be over 25 meters. And the Y component has to be up 16 meters. So our vector needs to be, something along the lines of that, right? It needs to be a vector needs to be directed in this direction, and maybe we can draw what that would look like. So A would be a vector that would go something like that. Now, we could figure out what A is graphically by drawing this 25 and this 16 to scale, taking a measurement of A, and then also finding this angle using a protractor. But we're going to reconstruct from components using another method that is not graphical, that relies on two things. The first is the Pythagorean theorem. And we're going to use the Pythagorean theorem to determine the magnitude. I mean, you're probably familiar with this. It's just saying, well, I can find the length of A as the hypotenuse by calling this like A and B and the hypotenuse C, and saying that C is equal to, or C squared is equal to A squared plus B squared, or C is equal to the root of A squared plus B squared. And we can crunch that out here. C is equal to, therefore, the root of 25 squared plus 16 squared. And if I do the math on that, 25 times 25 gives me 625. 16 times 16 gives me 256. I add those two numbers, so I get 881. And finally, if that's C is equal to the square root of that, or C squared is equal to 881, I need to take that square root. So the square root of 881 gives me 29.7, let's say. All right, 29.7 meters. I guess with proper significant figures, I would round that to 30, right? Because I have two significant figures coming in. All right, we can probably assume that this is not 25.3 or anything like that. So, all right. This lets me determine the magnitude of A. So A is a vector that is 29.7 meters long. But a vector is defined by not only a magnitude, but also a direction. So there's one more step. And this is a little bit maybe less familiar, I don't know. But the one more step that we have to do is we have to use the inverse tangent to find the direction. So let's talk about how to do that. All right. Well, going back to our SOHCAHTOA, right? We have this equation that says TOA, which is, it stands for this idea that the tangent of theta is equal to the opposite over the adjacent. All right? So if we want to find what this angle is, theta here, and we know the opposite over the adjacent, that's what the tangent of theta is equal to. So I can write this out. I can say that the tangent of theta has to equal the opposite, that's 16 meters, over the adjacent, that's 25 meters. Right? The opposite is the opposite side from theta. The adjacent is the other one that's not the hypotenuse. And I can find what this is equal to. 16 divided by 25. No sweat. .64. So if the tangent of theta is equal to 0.64, how do I get theta by itself? How do I undo the tangent of theta? And this is how we do it. We have to do the opposite of tangent. So on both sides, I'm going to do the inverse tangent. All right, so I'm going to write that this way. I'm going to say, I want the inverse tangent of this side, and I want the inverse tangent of this side. All right, let's okay. Over here we have inverse tangent and tangent. Those two are opposites and they cancel each other out. And so all I have left on this side of the equation is theta. On the other side of the equation, I have inverse tangent of 0.64, and here's how we do that. We use our second key on our calculator, and then the tangent. That brings up this tangent to the -1 power of 0.64. That gives me 32.6. If your calculator is in degrees like mine is, here I'll show you. The sine of 90 should equal 1. It does on my calculator. If your calculator is in degrees like mine, then this theta value that you get will be in degrees. That is to say that theta here is equal to 32.6 degrees. And this is how you can find both the magnitude and the direction of a vector if you are given its components, x and y components. All right, I think that'll do it.